Essentially this so the second problem here is kind of like a tree problem. So you start with so the problem is about you start at the node 1, which is you can treat is as a root. So on each node there's some grass growing in each second. So traversing one edge takes you 1 second, and then you kind of like want to fertilize all the nodes here. So you don't want to reach a node too late, because you kind of like want to fertilize it as soon as possible, since it will grow kind of like AI units. So I node will kind of like have AI growth each second. So essentially you kind of want to like traverse them like smartly, so that you can kind of like reach that grass when the like grass is still like has really small amount. So you're given this is kind of like actually two different problem here, where t equals to 0 means that you can you need to end with node 1, right? So essentially after traversing things along the way, after you fertilize all the grass, you kind of need to go back to where you begin. If t equals to 1, then you don't have to. And in each case, you kind of want to minimize the amount of time that it takes to fertilize everything. And then you also want to and you want to break ties by minimize the amount of fertilizer needed to like fertilize all those grass. So that's the thing that I mentioned earlier, where you want to avoid those grass to grow too much. So let's start with a easier case where like t equals to 0 here. So let's first look at like how we're gonna traverse this kind of like graph, right? So essentially you're given a tree as what I did before when I was drawing traversing passing this graph. You probably have a sense of like how I might traverse the tree, right? So essentially, I'm actually for each edge I'm gonna traverse it exactly twice, right? It's just like a regular DFS, and it's gonna be a little bit different when you're gonna choose which kind of like node you are gonna visit over a bunch of choices. But essentially, you will perform some kind of DFS where you kind of like traverse them in this manner, and then you kind of like after you visit the subtree, you kind of go back. So you will visit each edge exactly by 2 times. Right. And so that's exactly the minimum amount of time that you need to fertilize every pasture and then go back to node 1, right? So in this case, the time here will be 2n minus 2, right? So n minus 2 is n minus 1 is the number of edges, and then you want 2 times that amount to actually complete the whole thing, right? The amount of the fertilizer is slightly more tricky. So suppose, okay, so essentially now you have an order of kind of like traversing things, right? You want an order, so to traverse things that, so in each node you kind of want to choose, okay, I have several choices of the next node that I can traverse, like which one I am gonna do, right? So this kind of reminds us probably some kind of like greedy algorithm, or kind of like essentially we want to optimize our choices, right? So I'm gonna bring up something that we actually did before in December, which is kind of like some sort of like exchange argument. So suppose you have 2 choices, A and B, right? Or probably U and V, essentially 2 nodes that you're going to traverse. So suppose you are visiting this node already, and then you can kind of like choose U or V to be your next step, right? So suppose you traverse U, then which means you need to suppose you traverse U first, and then you need to finish all the things after before you kind of like traverse V. If you traverse V first, you kind of like need to finish all the things in the subtree of V first. So to reason about those kind of things, you might want to form a kind of like cost analysis, like what you will lose or what you will gain by visiting something first, right? So let's say we already fixed how we're gonna traverse this subtree here, how we're gonna traverse our subtree here. So once we have done that, actually moving like visiting this first will give you, so let's define two things. Size v to be the subtree size of v. So essentially like the number of nodes in. So and then sum v is the sum of ai in subtree of v. Let's see how those two variables might play a role here. So if we visit, say we have u and v here, if we visit this first, which means compared to visit this first, we kind of need to have 2 times size u, 2 times size u time later, like if we want, like compared to we visit this first, right? So what I'm saying is the time that we can visit u is kind of like postponed by this amount, right? Because we need to traverse those first. And by this time of traveling this, the graphs of here have already grown by amount of sum equals to v, right? So you can think of this as like a punishment of like going to this tree first, right? So similarly, we can see, okay, what's the punishment of go to this tree first? It should be like 2 times size of v times sum u, right? By similar reasoning, right? If you traverse this first, all the things here will grow by like sum u, and then it'll grow by size v, 2 times size v time units, right? So as you can see, like it is better to traverse this first, like the subtree of u first, if this is smaller than this, right? So after playing a little bit here, you could see that, okay, a better way to put this is probably like size u over sum u smaller than size v over sum v, right? So that if the ratio of the size and sum is smaller, which means it's better for you to actually go to that subtree first. So the thing that you can end up doing is like you can just like kind of like sort the subtrees by this, and then you kind of like visit them one by one here. So and also one thing to note that when you are choosing the optimal solution of like which subtree you're going to visit, you kind of don't change the way that you, like, no matter how you choose which one to visit first, you don't really change the way that you're going to visit those subtree independently, right? Either you choose this or this first, when you're going to this, it doesn't really change the way that you kind of like, or doesn't change the optimal solution where you kind of like solve the independent subtree here, right? So what you can do here is kind of like do a tree DP here. Essentially, DP V is the amount of fertilizer. I'll not write this, but DPV essentially is the amount of fertilizer that the minimum amount of fertilizer that you need to use to actually traverse the tree and fertilize all the grass, right? So suppose you have compute those values for things, and then you know that, okay, I'm going to traverse, and DPV is for like if you visit V in time 0. So visiting V in time 0, right? It's kind of like relative time as you will see later. So essentially, suppose you have a bunch of value for the DP already for the subtrees, and then you're gonna make a decision here by pulling out this, right? You're gonna visit the subtree with smaller ratio first, and then once you fix the order, right, you're gonna visit them one by one, and then the answer here will be, suppose this is like V1, V2, V3, V4 here, then the answer here will just be, you're gonna visit this first. So suppose that they are already ordered by this like ratio for V1, V2, V3, V4. Then the value to do this is essentially DPV1 times plus AI, some VI, because you kind of like delay them by 1 unit here, and then you're gonna plus DPV2. Essentially, you're gonna delay this by things. So the thing here, one way to make it really clean is that, okay, so DPV1, DPV2 is something that you would definitely need to pay when you visit this subtree, right? The only thing that might make things worse is the amount of time that you are delayed when you are visiting this, right? So for here, you can kind of like calculate, okay, suppose we have value here. We first sum those things up, and so this is the sum of DP value in the subtree. And on top of that, I need to add my penalization of like the delayed visit. So essentially, in this tree, I'm gonna delay by 1 unit because I need to traverse this, right? And in this tree, I'm gonna delay. So for the first tree, I'm gonna delay by amount of 1. For the second tree, right, it's slightly more complicated because I need to traverse this first and go back and then go to here. So essentially it's 1 plus, sorry, this should be times like some VI here, and 1 plus size, and actually 2 size, 2 times size V2 or V1, right? Because you kind of need to delay your visit by all the time you need to traverse this subtree and then go back to here, right? So this is essentially, you need to times this coefficient with some V2 because they will grow each by some V2 in each unit of time. So similarly, you will get this plus this times some V3, right? So on and on, right? So as you can see, you can kind of like calculate this in linear time, by time linear to the amount, the number of like children in each node, because you can kind of accumulate this along the way, and then this could be done in a DP or something, right? So once you sum those two terms up here, you will get the DP value of V here using the value of its children, right? So now I have described a really good way to, a really concrete way to do DP on this, which will give you a linear solution here. To actually not exactly linear, because you need to kind of like sort each level, which costs you n log n in total, and then log n in total. So in the end, you will kind of like get DP1, which is the answer to the final solution, to the solution to the final answer. Like, yeah. So this is just to remind you that DP is kind of like the minimum amount of fertilizer that you need to actually fertilize all the things and go back, right? So this is for t equals to 0. Any questions? Okay, so the next thing here is how to solve t equals to 1, right? It's kind of like a little bit difficult here, or like less simple than t equals to 0. So essentially, you're again traversing a tree here. However, you still want to minimize time, so you're gonna so let's say suppose you visit this and you visit this first. You need to go back because you kind of like you still have something that you need to visit. And you can visit this first, and then this and this, right? So the last thing that you visit must be a leaf, right? Because you kind of like reach a leaf and then you don't want to go back. And compared to the previous thing that we said, like traversing each edge by twice, you can save your path on this, right? So this is the distance that you save, right? So essentially, the amount that you save, the maximum amount that you save is the maximum depth or the deepest, or you can try to visit the deepest leaf so that you can save the most of time back, right? So this is in comparison of the previous t equals to 0 case. And so in this case, you will have to choose a deepest leaf. So this is one of our reasoning. So t equals to 1 here. You're gonna visit the deepest leaf, but suppose there are two deepest leaf, you probably don't have a clear choice like how you should choose which one to kind of like visit in the end, right? So in the end, you're probably gonna kind of like smartly choose. So in this case, we're still gonna do a kind of like DP approach, where probably slightly more complicated. So remind a good thing that we already get a DP value of suppose so DPV is a kind of like the thing that we get before, like the amount of mean amount of fertilizer so that we start from V and end with V, right? We go back, right? So I'm gonna define another DP array, which called probably the DP prime, which is minimum amount of things, so that you start from V and you end with one of the deepest leaf. So this is a slightly different kind of definition, right? So we kind of want our DP value to actually capture this. We're gonna end with deepest leaf here instead of like going back to where we started, right? So let's think about like how we kind of do the transition here, right? So suppose we already have this DP array because of the t equals to 0 part, and how are we gonna calculate DP prime V in this case? Okay, so here we go. We again we have a V here, and then we have different subtree here. And essentially we're gonna we have several decisions to make, right? So first decision is like which subtree we're gonna end up at in the end by not going back, right? So because we are calculating DP V prime here, we're gonna end up in one of the deepest leaf. Yeah. So first of all, we need to see. Okay. So suppose the deepest leaf here is in those two subtree. Essentially, those two subtree probably have the same depth, deepest leaf, or same leaf with like deepest or same depth of the deepest leaf. So we're not gonna end up in other subtree because they are not having the deepest leaf, right? So suppose we're putting this in the end, right? Essentially, we're gonna visit those four together before, and we're gonna after visiting those four, we're gonna go back to itself and then traverse, move to the next one, right? So essentially, we're going to put this in the order of last visit. But in what order we're going to visit those four, right? So it's exactly the order that we wanted in t equals to 0, right? We're going to visit them in order of the ratio of size over sum, right? Size over sum, right? Because as you can see, given any subtree that we're going to visit it completely, we're going to exactly follow the comparative here. So we're going to sort them by their ratio, and then do the similar thing that we said before. We accumulate the sum here in ON, and we will kind of like put this in the end, because like essentially we'll add dp. Suppose this is v5 because we put it in the end. This is v1, v2, v3, v4. We can accumulate the sum for v1 to v4 as we did before, and when we accumulate dp v5, we will add dp prime v5 and plus the amount of delay that we kind of like suffer from delaying the visit of this by the sum of the subtrees. So this is exactly the same formula as I said before. And oh wait, this should be, we shouldn't add those two terms, but this is the amount of time that you got delay, and then times the amount of like grass in the subarray, in the subtree. Yeah. So we can enumerate the last tree that you want to do. So somehow in each layer you will need to do at most m squared. So m is the amount of children here. So in the end, in the worst case, you're gonna summing up all the subtree size, not subtree size, but children size. So essentially, this will be strictly or like at least like less or equal to n squared, right? So which is probably good enough for one of the it's not good enough for the subtasks. But I think when no pasture is adjacent to more than 3 rows, essentially in each case you will have like m equals to small or equal to 2, so which will give you a linear solution here, right? Because you in this case you will have like 2 times m, and then this is smaller or equal to 2m, right? So in this case you can get a linear solution for subtask like 3 to 6 and then 11 to 14. Yeah. So because in this case the complexity of your algorithm is n O(n). Okay, so far we are kind of like brute forcefully enumerate all the things here, and we have to recompute those things to get again and again, which is not that efficient. But as you can see here, you can see this kind of like form of thing is there's some good property about this, right? So suppose you have, so let's just sort, let's treat all the subtree as we want to visit and then we want to go back. So essentially we're going to have a total order of it, which is v1, v2, v3, v4, v5, sorted by their ratio, the ratio that we defined before, the comparator, right? And then in this case, so suppose you're going to move v3 to backwards. Essentially, so suppose you have compute this configuration saying that, okay, I'm just going to visit those nodes, those subtree with coming back one by one, and I have a total cost, right? So let's suppose we're going to remove v3 from this sequence, and then so that the time of visiting v4 and v5 could like shift forward, get shifted forward. Like how will the cost change, right? The cost will change by, okay, so you first eliminate the cost, you need to like do this, right? Because you're gonna push them back and then you're gonna visit without coming back. So you're gonna minus dpv3 here already. And then minus like the amount of time you wait for the actual grass to grow, essentially is 2 times 1 plus size v1 size v2 or something like this, times I'll put the multiply here, times sum v3, because this is the amount of actual grass that it grows, right? So this is the some of the some cost that you don't have to pay if you remove this, but also you get to shift those forward a little bit, right? So essentially you're gonna the total sum will decrease also by the sum of v4 plus sum of v5 times the amount of time that you got shift forward, right? Essentially 2 times size v1, right? Because v3, because you don't have to visit this anymore, and then all the times that you get to visit those 2 subtree got like decreased by 2 times size. So in this case, so that's our total cost that we can save. And after we do this, we can kind of like add the amount of time that we need to, the cost that we need to like visit v3 in the end without not coming back. So plus dp prime v3 plus like the sum of the size is at this. So essentially the sum of, actually let me just do this, size v3 here by 2, because you kind of like shift by a factor of 2, and plus 1 because like you kind of like to traverse the last edge here. So multiplied by the amount of thing that is in your subtree, right? Which is slightly complicated, but we have mentioned the last 2 terms before. And pay attention to this formula, right? Essentially, this is kind of like the size in the prefix, and this is the sum in the suffix, and this is kind of like a equal sum, a total sum here, which can be captured by just one variable here. So as you can see, if you kind of pre-compute some of the stuff like suffix sum of those sums and prefix sum of those size, you can kind of like get this formula in just O1, right? Which is really good because you can kind of like calculate what's the cost of like putting a certain subtree in the end in just O1 with some certain pre-computation, right? So in this case, you can kind of like effectively enumerate, okay, for each subtree, what's the cost of like putting it in the back. So in the end, you will only require like OM to compute for each layer, for each node, and M is the number of children in each node. So in the end, when you sum over all the MI, MI is the number of children of the ith node, you will get ON solution. You have to sort them, so it's probably like log MI, which kind of gets you like n log M, right? So just to recap, we kind of have this like really good way to represent the change of values if we kind of like put some certain subtree in the end, which allows us to actually do fast query of like what's the cost of doing that, and this allows us to actually enumerate all the possibilities of like putting the subtree that we want to visit in the end. So the total capacity will be like n log n here. Any questions or comments, or if you get any better solution, please let me know. It's also good to share with everyone here. So I will, if there's no other